The first one I'd like to discuss with you is the question 39. And the question says this. Imagine you have a matrix. Thank you. Imagine you have a matrix. I'm not really sure. I mean, somehow it says here square matrix. Before I come here, I was looking at this and I wasn't sure if it's if you have any access right now to tutorial book. I don't think it's actually it's essential here that the matrix is square. It might be a typo, but it's irrelevant actually. The argument I present, we can judge it later whether it works for the non-square matrices. So the question says, prove that the following statements are equivalent. And here's a list of statements. Question gives statement A says AX equal to AY if and only if X equal Y. And that is true for any vectors X and Y from Rn. That's the first statement in a list of statements. Second statement says the null space or the kernel of the matrix is zero subspace. Part C says the nullity of the matrix A is 0. Statement D says the rank of the matrix A is n. E says the image of the matrix is Rn. F says that the columns of matrix A make a basis in Rn. And that this is it. So these are 6 statements, and we need to see the equivalence of all of these 6 statements, and that's a part of the question 39. So there's no any other way to do it but step by step, checking every equivalence between every 2 adjacent statements, and here's my argument, which shows that A implies B. Look at this. So we're assuming that A is given, so A is true, and we try to conclude that the null space of the matrix A is 0. Look how I'm going to do that. Imagine I have a vector from the null space, from the kernel of the matrix. First, I'm going to interpret what that means. By the definition of the null space, it simply means that if I multiply my matrix by this X, it will be 0, 0 vector. On the other hand, I make the following trivial observation. This is just the interpretation of what the null space means. On the other hand, I make the following trivial observation that if I multiply matrix A by a 0 vector, that also will be 0 vector. It's a trivial observation. So by looking at this identity, I see a place where I can use this A equivalence. It says if A of A times X equal A times Y, this only could happen when X equal Y. And that's exactly what we see here. A times X equal A times, in the position of Y, I have 0 vector. So by using A, now I can use the A here, I can say that X is a 0 vector. So you see what happened? I chose arbitrary vector from the null space, and for such a vector, the only option turned out to be 0 vector. This is exactly the claim B. I'll do the opposite claim straight away. So YB implies A. Now we assume this is true, and I'd like to see this equivalence. In this equivalence, as a matter of fact, the implication this way is a trivial implication. If X equal Y, obviously AX will be AY. So the non-trivial part of this equivalence is this implication, and that's the only one which I'm going to argue. So here's my argument. Imagine I have AX equal AY. Then by simple rearrangement, I can say that AX take AY is 0 vector by taking AY on the left-hand side. Now, by the distributive law of the matrix multiplication, I can say equivalently that this is A times X take Y, which is 0 vector again. That's from here. And now, here we go. We have a vector here in bracket. It's a vector with the property that if I multiply this vector by a matrix, it returns 0 vector. This is a definition of the null space. It means that by the definition of the null space, it means that X take Y vector is in the null space. But the null space, by B assumption, it's a 0 subspace, so X take Y is a 0 vector, which is the same as to say that X equal Y. This is a place, this is a step where we use the assumption B. So if I just take this, I bring it here, and I rename it to B, That's the place where B was used. And that's my argument, which supports the fact that these two statements are equivalent. Now, what about B and C? B and C, we can argue in one go that B and C are equivalent, and the argument is simply by the observation that the nullity is simply the dimension of the kernel of the matrix. So if the kernel of the matrix is a zero subspace, the dimension of such subspace is zero, and vice versa. If the dimension of the subspace is zero, the only subspace with the dimension zero is a zero subspace. That's why the equivalence between B and C can be argued by this simple reference to this definition of the nullity. Equivalence between C and D, it's another reference, it's another simple equivalence. I mean, it is a simple equivalence when you argue it right now, but it's not so simple because you have to make a reference to the rank and nullity theorem, and that's not an easy theorem. By that theorem, we know that the rank of a matrix is the same, plus the nullity of the matrix is the dimension of the domain, which is n, by that theorem. So the connection between these two numbers, it's exactly the rank and nullity theorem, because if you sum them up, it should be n. So if one of them is 0, the other one should be n, and the other way around. If one of them is n, the first one should be 0. Now, the equivalence between these three, it requires some extra notations. First, I'd like to introduce the names for the columns of my matrix, because you see the columns, they directly reference in one of the statements, so I will use the symbols for the columns. If the columns of my matrix, if I give them names, A1, A2, AN, and by S, I will denote the columns as a set of vectors, like this. Then here's what I'm saying, look at this. The assumption D, that the rank of matrix is n. By definition, the rank is the number of non-leading columns here. If it is n, every column is non-leading, number of leading columns here, my apologies. If rank is n, every column is leading. Right, so it means that the columns are linear, so the D implies that S is linearly independent. But if S is linearly independent, and if S has the same number of vectors as the dimension of this space, it means that S is the basis. So it implies F. This is something which I call the second comparison theorem. So again, because rank is n, columns are linearly independent. If you have n linearly independent columns in n-dimensional space, it means that they are bases. That's the part F. So we just made a step from G to F, skipping E for now. Now from here we can conclude E, because if F is a basis, it means that the span of S, which is the same as the image of A, it is my Rn, and that is claim E. So we see I'm choosing a little bit convoluted way of showing the equivalence between these three. I just showed you that D implies D implies F, and F implies E, like this. If I want to finish my equivalence, I need to show that E implies D. That's the only piece which is left, and here's the argument for that. If I assume E is true, meaning that the image of A is Rn, look what it means. It means that the span of S is Rn. S is this set of vectors. It's basically the image of Rn. We don't know right now, when we're just assuming E, if we're assuming E, we don't know if S consists of linearly independent vectors, but we can make an assumption that we can take a smaller set, which I will call S dash, which is linearly independent, and which spans the same thing as S. So if my S dash is a smaller subset in S, which is linearly independent, and which spans the same thing as Rn, what can I say? Well, I can say this. Rn, it's an n-dimensional space. The minimum number of vectors required to span Rn is n. It's something which I call span comparison theorem. That means that the number of elements in S dash is n, and that is exactly the definition of the rank of a set. So the rank of the matrix A, it's the number of linearly independent columns in that matrix. S dash was assumed to be linearly independent columns, and the number of columns, I just wrote it here, we just concluded that, is n. That's why we have D.